Now, let us consider the pseudocode that implements this algorithm. For the sake of simplicity, we assume that the points in the input are given in the sorted order, from smallest to largest. We start with an empty set of segments denoted by R, and we start with index I pointing at the first point, which is the leftmost because the points are sorted. Now, we go through the points, we find the leftmost point. Currently, I is pointing to the leftmost point in the set, and at the start of the while loop, I will always point to the leftmost point which is still in the set. Now we cover it with the segment from L to R, which has unit length, and the left end in the point xi. So this is a segment from xi to xi plus 1. We add this segment to the solution set, and then we need to remove all the points from the set which are already covered. Instead of removing the points, we will just move the pointer to the right and forget about the points which are to the left from the pointer. So the next while loop does exactly that. We know that for any I that is larger than the current I, xi is to the right from the left end of the segment, because the points are sorted. So if xi is also to the left from R, then it is covered by the segment. So we just go to the right and to the right with pointer I, and while xi is less than or equal to R, we know that the point is covered, and as soon as we find some xi which is bigger than R, it means that this point is not covered, and all the points further in the array are also not covered. So we stop. And then we repeat again the iteration of the outer while loop, or maybe our pointer I is already out of the array of the input points, and then we stop and return R, which is the set of segments that we've built in the process. Now let's prove that this algorithm works in linear time. Indeed, index I changes just from 1 to n, and we always increase it by 1. For each value of I, we add at most one segment to the solution. So overall, we increase I at most n times and add at most n segments to the solution. And this leads to a solution which works in big O of n time. Now, we had an assumption that the points in the input are already sorted. What if we drop this assumption? Then we will have to sort the points first and then apply our algorithm points cover sorted. Later in this module, you will learn how to sort points in time n log n. Combining that with our procedure points cover sorted will give you total running time of n log n. Now let's look at our improvement. We first implemented a straightforward solution which worked in time at least 2 to the power of n. And it worked very slowly, so that even for 50 children we would have to spend at least 2 weeks of computation to group them. Our new algorithm, however, works in n log n time, and that means that even if we had 10 million children coming to a party, we would spend only a few seconds grouping them optimally into several groups. So that's a huge improvement. Now, let's see how we went to this end. First, we've invented a naive solution, which worked in exponential time. It was too slow for us, so we wanted to improve it. But to improve it, the very first important step was to reformulate it in mathematical terms. And then we had an idea to solve it with a greedy algorithm, so we had to find some greedy choice and prove that it will be a safe move. In this case, the safe move turned out to be to add to the solution a segment with left end in the leftmost point. And then we proved that this is really a safe move. It is very important to prove your solutions before even trying to implement them, because otherwise it can turn out that you've implemented the solution, tried to submit it, got wrong answer or some other result different from accepted, and then you've made a few more changes, but it still didn't work. And then you understand that your solution was wrong completely from the start. And then you invent new solution and you will have to implement it from scratch. And that means that you've wasted all the time on implementation on the first wrong solution. To avoid that, you should always prove your solution first. So after we've proved the safe move, we basically get our greedy solution, which works in combination with the sorting algorithm in time n log n, which is not only polynomial, but is very close to linear time and works really fast in practice.